So this is the first lesson in Unit 5, and we're going to cover chemical bonding now. In Unit 4, we looked at electrons and how they get structured in an atom. So we're going to extend that now and see how molecules are formed, so how two or more atoms bond together. So this is a picture of two different atoms, and I want to remind you that there are repulsions and attractions. So for example, this electron out here is being repulsed by that electron on that other atom, and maybe this one is getting repulsed by that one. Okay, so that there are repulsive forces, but at the same time there are oh, and I forgot, we also have this nucleus full of positive charge that are also repulsing each other. But the electrons are being attracted between the two different atoms. So between the nucleus and the electron in the other atom, there's some attraction, and likewise there's attraction between this nucleus and this electron. And so those forces together help us figure out or help molecules bond. So molecules bond because they reach their most stable state. The potential energy of a bond lowers the entire energy of the molecule. And remember, we always are looking for the least possible amount of energy. Everything is. So bonding has sort of two factors that are important to it. The amount of charge. Okay, so if, for example, we've looked at ionic bonds before, and maybe there's something that has a -3 charge that could be nitrite or something like that, and it might be attracted to, oh, I don't know, how about a sodium with a positive charge? So those charge differences make it important, and we'll see that even in atoms that don't fully form ions, that a charge is very important. And also, we looked at, in Unit 3, the distance between the two atoms and how important that is. And in fact, we've looked at this particular slide in Unit 3 some time ago. And in this slide, what they're showing you is way over here, they have two atoms. They're pretty far apart, and they really have no interaction up in here, or very little interaction. Or here's the other extreme, where two atoms are so close together that they end up being repulsed by each other and split apart. Then there's the perfect distance. So in this, I think this is hydrogen, I believe. In this particular molecule, these two atoms are exactly at the right distance. Okay, so that exact distance allows them to have a good bond. And notice that this energy is going down as they get to better and better, or the right distance apart. So we've looked at that in Unit 3, and we've also looked at a little bit about bonding before. So we've looked at the ionic bond, and remember, ionic bonds are formed between a metal and a non-metal, at least almost always. The only exception there is the ammonium ion that can form a ionic bond as well. Everything else is a metal and a non-metal, but this is NH4+, that is an exception. At any rate, here is the sodium. The picture here is showing you that the sodium has lost an electron, and the chlorine has become a chloride by gaining an electron, and together they form an ionic bond. Now, these are discrete atoms that are charged, but they are attracted to each other because one's positive and one's negative. Then I wanted to look for a moment at metal bonding. Metal bonding occurs in a sea of electrons. So this picture is showing you all of this kind of fuzzy business on the picture is indicating that the electrons that go with each metal atom are delocalized, and they're spread all across whatever that metal is. And so that's a delocalized set of electrons that's spread all over the metal. And we're going to see more delocalized electrons later, but we're really not going to consider very much more on metallic bonding for now. What we're mostly going to focus on in this chapter are covalent or in this unit are covalent bonds. And covalent bonds occur between two or more non-metals. In your periodic table, those are the things in yellow. Two or more nonmetals. Now, we're also going to see that there are a couple of metals that have a little bit of covalent character, and they can undergo some types of covalent bonding, but typically two or more nonmetals. And what happens in a covalent bond is here's a chloride, a chlorine, and a bromine, and they end up having a bond where they share their electrons. So each atom contributes an electron, and they share a pair of electrons, which we'll look at in a moment. So a guy named Lewis put together this idea that when atoms bond, they lose, gain, or share electrons to attain an outer layer of 8 electrons. So that outer shell is going to have 8 electrons. So as we just saw, for ionic bonding, you lose and gain electrons when ions bond. For covalent bonds, you share the electrons in the bond. Each atom gets to count that electron that it's sharing as its own. So it counts the bonding electrons as its own, and that gives it a chance to achieve this octet that we're going to talk about extensively in this unit. I do want to note that hydrogen is an exception to that octet. It still gains the electron configuration of helium, which is a noble gas, of course, but there's only 2 electrons. That's an important rule. Hydrogen can only have 1 bond. Whichever way things get bonded, they always are trying to reach their minimum amount of energy. So for ionic bonding, let's look at that 8 electron rule. So when, for example, they're either going to reach NS2, which is basically hydrogen, helium, or they're going to reach the octet, which is another noble gas, any of those noble gases at the end of a period, NS2, NP6, where N stands for any period number. And then we'll see a couple that take on a pseudo kind of stability where they have their d orbitals filled. So for example, sodium, when it's in its electron configuration as sodium, it's a 1s2, 2s2, 2p6, 3s1. But when it loses that 3s electron, loses the 3s1 electron, it reaches the same configuration as neon, 2s2, 2p6. Magnesium, with a 2 plus charge because it's in group 2, also reaches that octet. Or here's F minus. F, come up a little bit, F in its regular electron configuration, so fluorine is 1s2, 2s2, 2p5. But when it gains this electron, it becomes very stable, like a noble gas. And you'll remember we looked at these and we call them isoelectronic series, so that ions, at least the main group ions, not so much on the transition metals, but ions from the main group reach the nearest noble gas configuration, the nearest noble gas. I did want to mention something, for example, like tin. Tin is, I believe that's a 6s2, 5d10. 6p2. I think it's in period 6. When it becomes 10-2 plus, it actually is going to be a 6s2, 5d10. But notice that it has a filled transition state level on the d orbitals, and that's a pretty stable ion. Now, I just wanted to kind of remind you, we've looked at this before, that when you have a solid, the solid is a crystal when it's an ion, and these are each a discrete charged atom. And they don't, and so they're only attracted by the charge. When you put them in water, okay, so when you make them into an aqueous solution, they'll dissociate into the water. And notice that, here's something that's positively charged. It is surrounded by a set of water molecules. And notice that the minus charge, which we'll see from the oxygen on water, is oriented in such a way that it's countering that positive charge. And likewise, let's do it in this color. Here's something with a negative charge right here, and the water molecules have some positive charge, and we'll see why later, but those are countering that negative charge. So the water is oriented in such a way that it helps counter the charge on those ions in water. Actually, going to skip that. All right, so we're going to now focus mostly on covalent bonds from here. So covalent bonds, as we've seen, have share two electrons. So there's always going to be an octet. So each atom achieves an octet, except for hydrogen. Remember, it can only have 2 electrons. And to get to the lowest possible energy, it has the least number of bonds that it possibly can. So, bonding occurs in covalent or molecules because they share an electron in an atomic orbital, where those atomic orbitals are thought to overlap. And there's 2 possibilities for this to happen. One of them is where one atomic orbital shares its electrons with another atom. It has both of the electrons. Oh, there's 2 electrons in any bond, and one atomic orbital has 2 electrons, and it shares those electrons with some other atom. We're really not going to spend much time on that in this class right now. What we're going to focus on is the second type, where both atoms have an atomic orbital that has 1 electron, and they're going to overlap and share those 2 electrons between themselves. So this is ionic. I just wanted to put this up here to show you that these are discrete atoms. And then this is the covalent idea. And in this covalent bond between these two molecules, you'll notice that, well, here's a nucleus, and you'll notice that in the electron cloud, they actually overlap each other, and there's this area right here where they share an electron between themselves from each atom. So once again, I wanted to notice that this is two different atoms that have bonded together. And there is some amount of repulsion between the nuclei and some amount of repulsion between the various electrons. But there is attraction between all of these things because of the different charges on the electrons and the protons. And there is some perfect bond length that we just looked at. Now I want to think about this distance for a minute. So this is a different picture, again, of two atoms that have bonded. So what is this distance? This distance is something called the atomic radius. And that is the distance between two nuclei. Then, when you're considering what the radius is, you take 1/2 of that distance. That is how we work out what a bond length is. Now, I told you that charge is really, really important. So how is it that covalent molecules get charge? That's based on a scale or a measurement called electronegativity. Electronegativity is the relative ability of some atom, of an atom to attract valence electrons from some other atom. So this electronegativity isn't strong enough to actually remove an electron, but it does attract electrons. And we have a trend here where electronegativity increases going up the periodic table and increases going across the periodic table. And fluorine, this is in a different color, fluorine is the most electronegative. Fluorine has the greatest ability to pull electrons towards itself. While usually we use cesium, although I think francium has the same value, cesium is the lowest electronegativity. It has virtually no ability to pull an electron towards itself. I want to go back and make a picture for just a minute. So what do I mean by it pulls electrons towards itself? Let's assume that we have some atom A and some atom B. And imagine that these dots I have drawn here are electrons. So these are the discrete atoms. Let's assume that B has higher electronegativity than A. What does that mean? That means that A's electron is going to get pulled closer to B, so that the electron gets pulled over in this direction. Now, A still has the electron. It just doesn't have as much of the electron as it would have had as a discrete atom. So there is this lovely electronegativity scale. You need to be able to identify the trend. I'm not going to give you these values, but Pauling came up with a set of values. For example, boron is at 2.0 that give a relative amount of measurement of how much these different atoms can pull electrons towards themselves. So notice there's fluorine. It has a 4.0, really high electronegativity. And here's cesium and francium, really low electronegativity at 0.4. I also want you to notice a couple of other things. Here's hydrogen. Hydrogen is one of those weirdos that moves around. Okay, that's not a metal, even though it's over here in group 1. That's not a metal. It's a non-metal. It just happens to just have one electron. That's why it's in group 1. This has a relatively high electronegativity, and it's very close to carbon. So keep that in mind. I also want you to notice that period 2, I guess 1 and 2, have much higher electronegativity values than period 3. So notice that there is a great big jump in electronegativity between period 2 and period, it's supposed to say period 3. Then, at period 3, you'll notice that the difference between period 3 and period 4 is very small. Okay, there's some, but it's not very significant. So period 2 has really, really high electronegativity values. Then after that, although it decreases as you go down the periodic table, this decreases from period to period. It's not a significant difference. You should be able to identify this trend even though you're not going to have these values. Now there's two types of covalent bonding. There's something called covalent, or sometimes it's called purely covalent, and there's polar covalent. Now polar covalent indicates that there's a little bit of difference in the charge. So this is a hydrogen atom and a hydrogen atom. Notice that they have an electron here and an electron here. As they begin to bond, there's an area of their electron clouds where they overlap, and one of those electrons flips in the other direction, so you have one going up, one going down, and that is a bond. And since they're both the same electronegativity, and I don't expect you to know this number, but they're both the same electronegativity value, they're just they're just covalent. There's no charge difference between those two. Compare that to hydrogen fluoride or hydrofluoric acid when it's aqueous. In this case, we have, again, this hydrogen atom. It has the 1s electron, and fluorine has valence electrons in the p orbitals, remember, so that's why we have this dumbbell-looking thing. So this fluorine has one electron. If we were to draw the electron dot structure, we would have one electron, 3 pairs, 1 lone pair. Those 3 pairs don't do any bonding here, but this 1 lone electron can bond with the hydrogen electron, and you'll notice that there's an overlap between them. So hydrogen's electron, fluoride's electron, overlap and bond. Now, hydrogen fluoride is very polar. Okay, it's a very polar bond. That's because hydrogen has a relative value of 2.1 in the table, and fluorine has a value of 4.0. And so there is a difference in the electronegativity values. And even though the electron can't be ripped off by fluorine, it can get pulled very close to the chlorine. In fact, let's go ahead and I want to do another picture. So, hydrogen fluoride. Here's its electron. It's going to be very close to the fluorine from the hydrogen. And so this is a bond where the atomic orbitals are overlapping. But in this case, this fluorine is partially negative, and this hydrogen is partially positive. That means that there's a little more electron density on the fluorine than on the hydrogen atom. So that this is how we indicate polarity. The less electronegative atom gains something is partially positive, and the more electronegative atom is partially negative. And so you will see that these are indicated with these little partial signs on each atom. Another way that this can be shown is indicate the bond there, is by showing an arrow that points the direction of the electron pull, so the electron pull in this direction, and a little slash sign, like a positive sign, at the end that loses some of its electron charge. I will expect you to be able to identify partially positive and partially negative bonds. So let's look at a little bit more on covalent and non-covalent bonds. I want you to notice that there's a continuum here. And so as you move through the periodic table, things become very covalent. So down here we have purely covalent, and up here we have purely ionic. And there is this relative scale as you move through the periodic table where it's a continuum. Nevertheless, we need some way to make a decision about what's covalent and what's ionic, what's nonpolar and what's polar. So we have a scale where anything that's greater than 1.7 in the electronegativity values are ionic. If you have something that's between 0.4 and 1.7, we call that polar covalent, so that one of those atoms has more electron density than the other. And then we have purely covalent, where our scale is somewhere around 0 to 0.4. Now, while you're working on your problems, look at this table and work on those values, but I'm not going to be giving them to you. I still expect you to be able to identify the trend in some way. But let's look at some things we know based on these values. So, for example, sodium chloride. Now, we know that's ionic. We've done a lot of work with that, but let's prove it, at least according to our scale. The electronegativity value on sodium is 0.9, and on chlorine, it's 3.0. So the sodium ion and the chloride ion have a difference in electronegativity of 2.1. That value is always positive, so you don't have to worry which way to go. It's just going to be a positive number. And according to our chart here, that means it's ionic. It's greater than 1.7, and therefore it's ionic. So then let's look at hydrogen and chloride. Now we know hydrogen is in a weird place. It's over near the carbon, and it has a value on the electronegativity scale of 2.1. And again, the chlorine is 3.0. And so our change in electronegativity is 0.9. Well, according to our, oops, must have gotten off on the wrong side over there, but according to our chart, that would be a polar covalent bond. And it would also mean, because chlorine is higher in electronegativity, it would also mean that, I'll put on the electrons here, that the hydrogen's electron is much closer to the chlorine than it is to the hydrogen. So that hydrogen is partially positive and chlorine is partially negative. That's how you indicate that. Let's look at one more. For example, how about chlorine and chlorine? So I'll put on the electrons. And this one has a charge of 3.0 and 3.0, so our delta En is 0. And that means that neither one of these chlorine atoms has the ability to pull the electrons closer to themselves, and so that's a shared electron set of electrons, and so they're equal, and that makes them nonpolar. Oh, and I also wanted to make a couple of other things I wanted you to note. I want to talk about HF again for just a minute. If you look at the scale, this is a 2.1, and that's a 4.0. And so the difference on that, the delta En, is 1.9. Under our rules that I now don't show up here, that would indicate that this is an ionic bond. But, like I said, this is a continuum. Okay, so it's not ionic. It is actually polar covalent. Even though it doesn't quite fit our rules, we know from experiments that that's a polar covalent bond. And I also wanted to mention the carbon and hydrogen bond. Carbon and hydrogen. This is 2.5, I think. And this is 2.1. The delta En is 0.4. What I want you to take away from this is considered a purely covalent bond. Even though there's some little bit of electronegativity difference, in general, those are very strongly bonded to each other, and we consider that a nonpolar covalent. All right, so let's go over what's ionic and covalent again. So which of the following is an ionic compound? So I want to have a metal plus a nonmetal. So you might be tempted by H2S because hydrogen is in period 1, but that's not a metal. Okay, so it is not H2S. That would be something that's covalent. All of the rest of these, except Ki, are 2 or more nonmetals. But Ki is a metal and a nonmetal. That means that K will lose an electron and I will gain an electron. And in a solid, they'll be attracted to each other such that they're right next to each other. And in aqueous solutions or in water, they would be separated and surrounded by water molecules. Now, covalent molecules are 2 or more nonmetals. So using your periodic table, those are the yellow things in your periodic table, that lets out sodium, calcium, and cesium because all of those are metals The only thing left here is the dichlorine monoxide. And that would be a covalent compound. So electronegativity, a definition. I'm going to give you 30 seconds to read these answers and make up your mind which is which. All right, so let's look at these. A, energy needed to remove an electron from an atom. Well, remember that is ionization energy, which we looked at in the trends from the periodic table in the last unit. How about the energy released when an electron is added to an atom? Well, that was the electron affinity definition. So that can't be it. C is the magnitude of the negative charge of an electron. I'm not really totally sure what that means. So I think that's just nonsensical, although I could consider, for example, how much, if this was a positive instead of negative, that could be how much charge the atom feels, and that would be the effective, Z effective, or the number of protons it actually feels. The magnitude of a negative charge on a molecule. I don't know what that means at all. So that leaves only the attraction by an atom for electrons in a chemical bond. That's electronegativity. So I might ask you which is the most electronegative or which is the least electronegative. I could ask you questions like identify the most covalent bond to the least covalent bond, or vice versa. And so you want to have your periodic table when you answer these things. And since your periodic table will basically look like this without the colors on it, you need to be able to identify it from there. So which of the following atoms is the most electronegative? So in this case, you might want to go to your periodic table and just find these atoms. So we have sulfur on our list, Rutherfordium is here in the transition metals, silicon, Beryllium, where are you? I've forgotten where beryllium went to. You find it on my own periodic table. Oh, beryllium down here, sorry. And cesium. So that's the first question, is which is the most electronegative atom? Well, we know it's not going to be cesium. Okay, it's going to lose electrons, and we know that. This is also a metal. It has a lot more ability to lose than to gain. So that puts us over here. Well, remember the trend in electronegativity increases up and increases across. And so under that trend, sulfur is the most electronegative atom. On this group, if I had asked which was the least electronegative atom, you would have identified cesium as the least electronegative atom. So I want to clean this off, and then we're going to use this to answer the question about which is the most polar bond, the most polar bond. And so on that question, we have we're going to compare PF, BAF, ALF, NF, and BRF. So life is sort of nice here because I just have one, the fluorine goes with everything. So I'm going to find the other things. So phosphorus, aluminum, nitrogen, bromine, and barium. So find things, locate things on your periodic table so you can make a good comparison. Now, the closer they are together, the more covalent. And the farther apart, the more ionic. Or the less covalent, whichever way. So, in looking at my periodic table, I can see, and remember there's a massive drop-off, a huge drop-off between period 2 and period 3 in electronegativity values. So I'm going to consider the N as closest to the F. So I would call that NF the most polar. Which way are we going on this question? Most covalent. So that's the most covalent. Then I'm going to consider the fluorine and the bromine way over here. That's a metal and a non-metal, so I need more space. I'm almost afraid to do this. Let's see what happens to us. Okay, we've decided that NF is closest, therefore it's going to be the most covalent. And we know that BF is very far away, and so that's going to be the least covalent in this particular case. And then, let's see, the next thing that's close to the fluorine would be the phosphorus. So I'm going to put PF here. And then I have to consider what's happening to aluminum and bromine. They're both fairly far apart, and so I'm not sure. I don't know whether aluminum fluoride or bromine and fluoride are the next group. Now, you can find it on your table, but let's reason this out for a minute. Aluminum is a metal, and a metal and a non-metal are mostly going to be ionic. It turns out that aluminum has some covalent character, but the least electronegative atom here, the least electronegativity difference here is going to be between the fluorine and the bromine, and because that's a non-metal. Okay, so you could reason it out by thinking, well, bromine to fluorine is at least a non-metal, two non-metals, and then the aluminum, even though it's pretty close, and even though it has some characteristics of covalency, that's a non-metal, so I'm going to put that one next to last. Also, if I ask you to determine, if I wanted you to show me which is the most electron, or I want you to show me what's partially positive and what's partially negative, you can do that from the trend. Fluorine is going to be partially negative because it's going to pull some of nitrogen's electron density away. So nitrogen is partially positive. Fluorine is partially negative. You can also show it in this fashion where you show the arrow with the end that's got the most electronegativity, and then this kind of positive sign showing that electronegativity is lesser or partially positive on that phosphorus end.